Welcome everybody to another edition of Nano at Tech. This is the seminar series presented by the Institute for Electronics and Nanotechnology at Georgia Tech. Unfortunately, of course, we are online to start the semester due to Omicron, but hopefully we'll get back to in-person and streaming on YouTube in the not too distant future. Before I introduce today's speaker, let me just mention that the next speaker in 2 weeks, actually 2 weeks in a day, because it'll be a Wednesday seminar, will be on January 26th, Wednesday, 12 noon, and the speaker will be Professor Alper Erturk from the School of Mechanical Engineering here at Georgia Tech, and that will also be an online Blue Jeans presentation. So today's speaker is Professor Alan Doolittle. Alan is what we call a Georgia Tech lifer. He got his bachelor's degree here in electrical engineering at Georgia Tech, and then his PhD, also from Georgia Tech, and is currently the Joseph Pettit Professor in Electrical and Computer Engineering here at Georgia Tech. He also directs the Advanced Semiconductor Technology Facility. He's won a number of awards, notably an NSF Career Award in 2004 and a number of Georgia Tech teaching and research awards. And with that, I will turn it over to Professor Doolittle.
All right, so I appreciate the opportunity to speak. Today I'm going to talk to you about what I call creative epitaxy. Basically, this is more of a discussion, since I'm assuming most of the audience is students, about how you approach hard problems and how you address difficult challenges. And so basically, I want to give you some examples from my research, but the overall goal that I want to present is how do you do something that's really, really difficult? How do you approach things, for example, that some people would say are impossible? If you know me, you would know that I hate outlines. I view them as a waste of time. But since this is mostly addressed to students, I feel obligated to give some form of outline, and so I will do so here. This talk's going to have a beginning. It will have a middle, and most importantly, and probably what you're going to look forward to more than anything, is it will have an end. I promise you, it will eventually end. And as a example to the students that are out there, you should always reference any material that you take from someone else. And my good friend Jerry Woodall actually gave me this outline, so I do give him credit for this outline. The question comes up when you come to a situation where you see no way through, where you think something is impossible. What is it that you actually see? Are you looking so close at the problem that all you see is the barrier? Or can you step back from the problem and find a way around the issue? Oftentimes, when you find something that people say is impossible or extremely difficult, if you take a broader perspective, and I'll define what I mean by that in just a moment, you find a way around it. This particular guy here probably isn't too happy about having a hole in his wall, but nonetheless, if you step back, oftentimes you can see a way to get around these problems. So that's basically what I want to talk about today, more or less the bigger perspective of approaching difficult problems. And so before I do that, I want to give you a little introduction to me. I am oftentimes associated with a famous fictional veterinary doctor that talks to animals, but I will point out that that particular doctor here, this is the original Dr. Doolittle. Of course, Eddie Murphy reinvigorated that myth back in the 90s with his series of movies. But that particular doctor actually has a problem in that he misspells his name. But much like that fictional veterinary doctor that talks to animals, I have a two-headed animal, much like the push me pull you that Dr. Doolittle had in these movies. I work basically in two different areas. I work in the materials area of III-Nitrides, the semiconductor nitrides, and I work in the area of complex metal oxides. And the two oftentimes have greatly diverse applications and seemingly sometimes pull you in opposite directions. The other part of my work is involved in what we call molecular beam epitaxy. Some people like to call it megabucks evaporators because that's basically what it is. It's a fancy evaporation system. But basically, these systems involve using these heaters, we call it fusion cells, and you load them up with various metals. For example, this commercial system here might have the equivalent of 4 liters of liquid gallium inside this heater, or indium or other compounds. And you load those fusion cells into these little slots. This particular system has 13 of these slots around the periphery. And in front of those slots, they have a simple mechanical shutter. And you basically evaporate material that condenses on a crystalline substrate, and you recreate the crystal structure of that crystalline substrate up here on some wafer that would be located roughly where my pointer is. This particular system is able to grow 76-inch wafers at a time, or 144-inch wafers at a time. And these things are used primarily for high-end lasers, like for communication systems and high-end transistors, things that other growth technologies cannot quite achieve. Now, this process of epitaxy, I want to define this for sure for the students in the room, or online in this case, is the idea of repeating a crystalline structure by an atom-by-atom addition. And so you throw a whole bunch of these elements at an existing crystalline substrate, and you let Mother Nature kind of sort them out. In particular, gallium bonds, for example, if you're growing gallium nitride, will only bond to nitrogen, and gallium to gallium or nitrogen to nitrogen bonds will not be favored because Mother Nature doesn't allow that by her chemical rules. So when we do that, what we're doing is we may add some gallium, add some nitrogen, then add some maybe aluminum instead of the gallium, add some nitrogen, add some aluminum and gallium mixed together, maybe 25% aluminum, 75% gallium, and keep doing that. And what we can create is what we call a bandgap engineered structure with this epitaxial process. If you compare, say, the alloy mix on the left-hand side versus the band gap, the conduction band on the left and the valence band on the right, you'll see that when you get to the aluminum bearing materials, the band gap is actually proportional to how much aluminum is in that material. With this approach, you can do fancy things like make quantum wells to trap electrons and holes in the same region, enhance light production. You can create 2D sheets of charge associated with like transistors for conductance, for high frequency transistors. You can even do fancy things like start an electron, say, in the conduction band here where my pointer is, launch it into the lower band gap material, and as soon as it leaves this region of high band gap to low band gap, the potential energy of the band gap is then converted into kinetic energy, and that launches an electron at phenomenal speeds, and this is useful for high frequency transistors. So there's a lot of things you can do with these band gap engineered devices. So with that kind of introduction to who I am, what I do, what my interests are, I kind of want to turn now to an actual hated outline. I cannot stand outlines, but for this particular purpose, I think it's important. So the first thing we want to address is how do we approach the impossible, okay? I want to do this by first laying some ground rules, and then I want to give you 5 examples of things that people said were impossible in the III-Nitride area, and we have actually been able to achieve them. And the way we achieve them is by the analysis that I would define in the first bullet point. I then want to go into looking at perhaps the ultimate impossible, is that can we engineer material systems that are inspired by the human brain? I'll just give you the answer ahead of time. I believe we can. I really am very confident that there are really good alternatives to computing that are out there that can compute very much like the brain does. And finally, I will give you, time permitting, some examples of failure. I may not be able to get to this, and I'll apologize if I've run out of time, but I think it is important whenever you're giving a presentation that you don't leave people with the understanding that, hey, everything always works out, all these great successes is all that's ever happened. No, we've had some really glorious failures too, and I think it's important to give students a perspective of what we learn from these failures as well. So first, a general philosophy on the topics that I pick. I absolutely hate the idea of eking out like 1 or 2% extra performance in an existing device that somebody else already has out there. And so I kind of always pick topics that are kind of according to this philosophy that, you know, if you're not the first horse in the line, your view never changes and life really, really stinks. So I prefer to be the first one doing things out there. And so we pick topics that no one else is working on, oftentimes because they view these things as impossible. All right, so what do I mean by impossible, and what is our approach to impossible? Well, the first question you want to ask is, does the impossible that people believe really violate a law of physics? If it does, well, it probably really is impossible, okay? But oftentimes people will say something's impossible, but they don't realize that there's these inherent assumptions in what they're looking at that really the impossibility is based on these assumptions. So if you define what the assumptions are in an impossible situation, then you can ask yourself, how can you violate these assumptions, okay? And oftentimes when you can violate these assumptions, you find a way around that thing that people view as impossible. So that's the key to the approach. Now, many times what is impossible is not really impossible. It's impossible with the current set of tools you have in hand. So as an engineer, we oftentimes find ourselves having to make our own tools to do the things that we need to do. You can't just go out to Walmart and buy some of these tools that we need. Now, with all that said, these are the key aspects to do, but really what we're boiling this down to is you have to know your problem inside and out. And so a lot of students like to, bypass the derivations of where equations came from or where the history of a system was or the history of a material was. But actually, that's the key aspect. Knowing the material system really backwards and forwards is really the key to finding out what these assumptions are and hopefully bypassing. Now, all that said, the scientists might be happy with just doing something that's impossible. They may want to build a $1 billion neutron source to examine new things without knowing what would come out of it. But as an engineer, we have to ask the question, if I can do what I think others think is impossible, what is my gain and is it worth the cost? If it costs me $1 billion new tool, am I going to get $1 billion worth of new research ideas or new device innovations or some sort of benefit to society outside of that? The scientist would always say, who cares? I'm still going to do it anyway. The engineer kind of has to do this techno-economic analysis as to whether it's worth doing or not. So to that end, you kind of have to go back to the oldest joke in the world, probably. The guy comes to the doctor and says, "Doctor, it hurts when I do this." The doctor says, "Don't do that." Well, if it hurts too badly, if it costs too much, just don't go down that path. And that's kind of an analysis you have to do up front when you're approaching a new topic. Okay. So with that kind of introduction to how we approach the impossible, I now want to kind of turn my attention to some examples of things we've done with it that people said were impossible. Now, the first one is related to the growth of these III-Nitride semiconductors. Now, universally, even to this day, when I go to a conference and present, there is always someone in the audience that says you cannot grow these III-Nitride semiconductor materials at low temperature. And it's totally based on folklore. It's not at all based in science, but that's the perception that people will have. So there are some tricks to it, and I'll talk about that now, but basically the argument is they confuse what's really going on the surface of their epitaxy tools. So if we consider two atoms, one on the surface shown in red and one in the gas system, say for an MOCVD system or a CVD system in general, what ends up happening is with these nitride materials, if we are nitrogen rich, we have these enormous energy barriers for diffusion on the surface because the energy bonds for hopping from one site to the other on a wide bandgap semiconductor are just astronomically enormous, 1 to 2 eV or even greater. So what happens here is that we get a lot of gas diffusion. The atoms move really far across the surface and intermix on the surface randomly from the gases impinging on the surface, but it's extremely hard for the atom to hop over these very large energy barriers. So how do you violate that fundamental limitation and get more diffusion on the surface? Because remember, in a gas environment, in a vacuum environment, an evaporator, you don't have the luxury of this long diffusion length in the gas phase. So the idea is to convert the surface not from a semiconductor bonded surface, but add an extra layer of metal onto the surface. And metal bonds are very weak, so the bond energy, the hopping barrier between hopping is very small, and the atom can very readily diffuse across the surface. It's not uncommon for these particular bond barrier heights to be a fraction of an electron volt, something like 0.1 to 0.2 electron volts, for example. Now, when I first started doing this, it was literally thought of as sort of heresy and crazy. And it's still, to some degree, people still, as I said, the people that are uninformed really don't believe this is possible. But it is really true that you can do this in practice. And I won't go into the details here of you know, where it came from, why we do it, and so forth. It's actually an interesting history of learning from your elders, if you will. I picked this up at the very first nitride conference that I ever went to from a respected man, and I just stayed with it. I believed what he said, and I applied it throughout my career, and it's paid off in enormous value. But the bottom line is this. We really looked at it this way. When we do epitaxial aluminum, growing single crystal metals, we do that at 100 degrees C. But if you turn around and do semiconductor bonds, no longer metals, but aluminum nitride, for example, which is an insulator with 6.1 eV bandgap, so it's enormous chemical bonds on the surface, you have to do over 800 degrees C in a vacuum environment. That's basically, you'd love to do it hotter, but you just can't get that hot in these vacuum systems. In CVD systems, they may do 1100 all the way up to, you know, in PVD systems, all the way up to 2200, 2400 degrees C to get this to work. But the truth is the surface bond strength dominates over temperature in epitaxy. And it goes something like this. There's a particular hopping rate that has a constant out front, a barrier height associated with what we were just talking about, and then the temperature, the thermal energy in the denominator. Now, this term actually feeds into the surface diffusivity term. And basically, you're not worried what the temperature is. You're concerned about what this ratio is. So if you have a small barrier height, that works the same as having a large temperature. And when you do this numerically, you find that there are about 10 orders of magnitude difference between the barriers for, say, a metal-on-metal type of surface versus a nitride or semiconducting surface. And even if we go to, say, comparing 1100 or 1050 degrees C here, roughly speaking, versus 600 degrees C, there's still 6 orders of magnitude difference in the hopping rates of these atoms on the surface because we have lowered the barrier height. Now, if you go into the literature, this basically is saying we're approaching the mobility regime where this ratio is approximately 1. That's kind of the science behind it. So we do get phenomenal atom mobility. Now, the next thing people will say is, well, you always have to have a lot of point defects in low temperature grown material. That means missing atoms, vacancies, things like that. No, you don't. If you're spreading the atoms around on the surface and they're diffusing long distances, it doesn't matter what the mechanism, if it's gaseous or if it's, you know, moving on the surface, you still have the same mobility, if you will, on the surface. And more fundamentally, if you look at the any material, the number of vacancies that you have is related to the atomic concentration and an activation energy for forming that vacancy. What that says is actually you get more vacancies as you go up in temperature. This is a fundamental material principle that people misquote and say the exact opposite to say that the material quality is better at high temperatures. What is true is the material quality is better with long diffusion lengths on the surface. That is true. But you can get those diffusion lengths without having to sacrifice having these vacancies by growing low temperature with these metal covered surfaces. What this results is, regardless of whether we're growing indium nitride, gallium nitride, or aluminum nitride, we grow substantially lower temperature than traditional MBE or MLCVD with this approach, what it boils down to. Now, how do we do this? If we've got this metal coverage on the surface, we could have potential problems, because if we have more than, say, one monolayer of metal or two monolayers of metal, two molecular layers, two atomic layers tall, what can happen is you start to build up these droplets that kind of segregate into little clusters of metal, and they shadow the growth. And you certainly can't have droplets in a device. So what we end up doing is we actually oscillate between the droplet and metal-rich regime, and then we cycle in and out of these nitrogen-rich regimes. So we're constantly adjusting the flux of the surface, or the metal content on the surface. Sometimes we have high diffusion length, sometimes we have low diffusion length, but when we have low diffusion length, we're also drying up the surface to ensure that we never have these droplets form or have metal in our devices. Now, this has actually been able to produce phenomenally fast growth rates. Put this in perspective, molecular beam epitaxy typically grows about 0.1 to 0.2 microns an hour. And this actually has a lot of benefits for a vacuum system. For example, if you grow faster for the same background impurity system, you have lower concentration of background impurities. We also grow dramatically good material. These are actually little atomic steps on a surface here. You can literally see the ledges of an atom by atom step as it moves across here. This is a great surface here on this thing. We can look at a Fourier transform of the surface, and basically even this is so flat that we can actually see when the atoms kind of rearrange themselves on the surface in a different geometry on the surface. Quite remarkable how good of quality you can get. Another example here is indium nitride growing at over 4 microns an hour, and you can see the very clear surface steps here. State-of-the-art X-ray rocking curve widths here as well. This X-ray rocking curve width is a figure of merit for crystal quality. And you can even see where these little dislocations, which are little holes in the substrate coming from the substrate itself, this is a defect in the substrate we grow on, actually perturb the growth of the indium nitride film. So it's trying to be better than the substrate can allow it to be, if you will. Now, essentially what we've done is that Mother Nature has given you some basically 4 stable phases for these nitrides. And I should point out that most other material like gallium arsenide, indium phosphide, use one phase. You have one phase here. Nitrides are a little bit more complicated. They have these 4 stable phases. And we've added some transient versions of this. So we actually have a significant portion of our growth time is actually in between these 2 phases. And the same thing with these others. So we've introduced 3 other phases. And it turns out that these other phases are actually best for, some of them are best for P-type doping. Some of them are best for growing ternaries like aluminum gallium nitride or indium gallium nitride. Some others are best for growing the best crystal quality of a binary like gallium nitride or an indium nitride, and the best for N-type doping. And if you optimize those growth conditions, you can do some pretty amazing things. Now, that was a long version of one of the impossibles that we did, but it basically sets the stage for the next 4. The next one people said is, hey, you know, indium gallium nitride, it has a different lattice constant than the substrates you can grow on. And that means that the atoms don't align up, so you're always going to have these dislocations that kind of push through the film and end up in your device. That's actually not true. We have found ways that you can actually, you always do have to have dislocations. That's true to relax the strain. But we have found ways to actually turn them over. For example, instead of threading through the device as shown in this transmission electron microscopy image, we can lay them in the plane between the gallium nitride and the indium gallium nitride, and that allows us to grow incredibly high indium content indium gallium nitride that very few people can do with very low dislocation density. At least in this particular scale, there's no apparent dislocations. If you go to a broader scale, of course, you do see some. So another one that people will say is, hey, you know, indium nitride and gallium nitride, when they form this alloy indium gallium nitride, those are immiscible materials. That means that like oil and water, they do not want to mix. Basically, indium's too big to fit into the gallium nitride lattice, and so it wants to separate out and form indium-rich clusters and gallium-rich clusters. This is called segregation. And in that case, everyone refers back to a paper from the late 1980s that basically describes this as bulk binodal decomposition, meaning that the material is literally falling apart once you grow it, because it's hot, it's diffusing apart, if you will. And the truth is that's a bunch of hogwash. The only thing that happens is what goes on the surface. Now, there are comparable separation processes that go on the surface of the growing film, but because these materials are so dense, bulk diffusion is practically zero in these materials. And if you grow cold, they actually are, it is zero. There is no bulk diffusion. So if you can control what goes on the surface, you can control this segregation problem. And we've done this basically with all of the ranges of indium that most everyone else thinks is impossible, from say 22% indium up to 72% indium. We get nice smooth surfaces, excellent crystal quality with state-of-the-art X-ray rocking curve figures of merit. And the way that we're doing this is we just grow fast, because we now have this option with this new approach to grow very fast. We basically are covering up the atoms. So the atoms come down randomized, and they would normally want to separate apart, form these indium-rich and gallium-rich clusters. But if we cover them up fast enough, what happens is they become a bulk atom instead of a surface atom, and diffusion stops. So you trap them in the random sites or near the random sites that they came down and landed on the material, and it works absolutely well. We've done this with indium gallium nitride. We've done this with aluminum indium nitride. And aluminum indium nitride, we have like 11 times better than anything in the literature in terms of X-ray rocking curves by using these techniques. Now, a big one in my career, the one that almost ended my career actually, was so controversial that people yelled at my students when they presented this the first time in a conference in Scotland. And people just could not believe that this was ever true. But our argument was that hole concentrations, hole is a carrier of electricity, a positive charged carrier of electricity in gallium nitride, could never exceed about 210⁸ concentration. And what they were saying was that the acceptors are so deep in these materials because Mother Nature dictates that the acceptor is so deep in these materials that I don't care if you put in 10⁻20 dopants, you're only going to get out, 10⁸18 holes. That was the argument. But we found a new way to do this. And the bottom line is people had lived with this rule of thumb that if you exceeded about 5 times 10⁻19 magnesium acceptors that you would put into gallium nitride, this would precipitate out and form these little clumps of magnesium. It's no longer dissolved in the crystal. It now is kind of clumped up in the crystal. And those don't act as acceptors. Even though you're getting magnesium in the film, they don't act as acceptors. Well, through the techniques I just described, growing fast, not allowing things to diffuse because you're growing cold, we've been able to put substantially more magnesium into the crystal and still keep it dissolved, where there is no evidence whatsoever of this clumping or precipitation. And when you do that, you get substantially more holes out of the material. This is over 20 times higher hole concentration than anyone had ever seen in the material. And that's why a lot of these very established researchers basically, to play the old game, they call BS on this. And we, of course, had to have outside confirmation of this and so forth and so on, which we, of course, had. So looking at the way these things have doped, using this low temperature form of growth, you end up having an N-type slightly better than the state-of-the-art, 2 to 4 times higher state-of-the-art than others. But for P-type, you not only have 40 plus times state of the art now, this is a modern number, not the one I was just showing you, it was 20, but you have dramatically different behavior. When you cool the device down, it does not freeze out, meaning the carriers don't go away, and which typically leads to high resistivity at low temperature. And if you look at the literature, all of the high doping values that are out there, the highest ones in the literature, all come from my group spanning a time basically up till to right before COVID, if you will. Now, the physics of this is kind of interesting if you understand why it works. In traditional doping, you end up having these magnesium acceptors that are so far apart because you just have a low concentration of them that you get an isolated acceptor energy that's well above the valence band, and because the Fermi level is below it, it remains mostly empty, so you don't get to produce many holes in the valence band. But if you can get the density higher and still have them dissolved into the crystal correctly, the Bohr orbitals of these magnesium atoms start to interact. They get close enough to where the Bohr orbitals interact. And so instead of an isolated acceptor, you start to form an impurity band similar to a conduction band or a valence band. It's a range of allowed energies that can occupy electrons. And some of these are below the Fermi level. And so what happens is your activation energy goes from something very deep, like 200 milli-electron volts difference between the activation energy, the red line, and the valence band, to something about 50 milli-electron volts here. And put that in an exponential, that makes an enormous difference in the hole concentration. And we proved this out with various luminescence techniques to where if you have an isolated acceptor like what might be grown for, say, an MOCVD or traditional MBE method, you get this deep transition about 3.2 eV. So from the conduction band down to here is about 3.2 eV. But if you do it with our technique, you get a much broader luminescence peak, and that luminescence peak actually penetrates into the edge of the band gap. So basically you're getting a mixing of the impurity band and the valence band in this case. When you do this, you can even operate your LEDs down to cryogenic temperatures because the holes don't go away. They don't freeze out in this way. So the last one I want to talk about is one that we've discovered in the last year. It's pretty remarkable. We have been able, and I don't want to undersell this, but this is a big deal. We have been able to create the widest bandgap semiconductor ever known. Aluminum nitride was previously known only as an insulator or substrate, if you will, but you could not make it conductive, not at least in the bulk layers. And basically by understanding the defect principles, the impurities that go in there, how the defects form and all this, and using these low temperature techniques, we have been able to demonstrate the first ever P-type conduction, and as of just a few months ago, now N-type conduction and diodes in aluminum nitride. So the hole concentrations now are exceeding 310 to the 18. The acceptor energies are about 37 milli-electron volts. They are 200 to 400 in traditional ways of doping. That's why you couldn't get any carriers out of it. We have changed that, and now we have the first evidence of conductivity at all in aluminum nitride, substantial conductivity, I should say, device level conductivity. And we've done the same thing now with electrons, and we'll show you that we have a first PN diode. I won't get into all the detailed physics because this is pretty involved. This one took a while to really conceive and act. But it basically involves using a different impurity, something that's closer in size to aluminum so that it doesn't strain the lattice like magnesium would when you substitute aluminum. And we've had contacts that we've been able to make. That's a whole nother set of problems there when you try to make contact to a 6.1 electron volt semiconductor. Rather difficult challenge. We've had outside verification, but let me just kind of show you how far this deviates from the norm. Aluminum nitride traditionally has grown between about 1100 and 2200 degrees C. These results were grown at 600 to 700 degrees C by adding this extra aluminum layer to the surface. And it has remarkable results. The first PN junctions, a diode literally made in what everybody else would call an insulator, turns on at 6 volts, which is right nearly ideal for the 6.1 eV semiconductor. It has about 6 orders of magnitude rectification. We're still working on some series resistance issues and a fairly low breakdown that you have in this device, but this is a first ever, so first is always first. You can be better, but you can never beat first. And all of these advances I've talked about basically have applications in things like water sterilization, particularly killing viruses like COVID, polymer curing, lithography, other things like that. Applications in lighting, replacing expensive solar cells that are like $50,000 per square meter for your compound semiconductor tandem solar cells with things that are like, less than $1,000 per square meter per subcell that you have. Now, real quickly, I'll just say we've done a lot of other things. This high doping has allowed us to do tunnel junctions, including the highest conductance gallium nitride tunnel junction, the only one that was ever reported on sapphire that actually worked, which is a cheap substrate, if you will. The first reported delta dope substrate. We've even got negative differential resistance in aluminum gallium nitride and tunneling in aluminum gallium nitride up to 58% aluminum. Now, what can you do with that kind of thing? Well, replacing contacts in deep UV LEDs. So a 270 nanometer LED is designed to kill viruses. Pretty important topic of the day. But the problem is they normally have very low power, in one part because you can't make contact to this aluminum gallium nitride because other people can't dope it well enough. So what we've done is we've replaced the contact with a tunnel junction that allows us to get carriers in and out. And in what we've seen is 110% increased power at that point, the green versus the blue curve. And there's more to come now that we have this aluminum nitride that we can do. I won't go into this, but there's some state-of-the-art Balaga figure of merits for power devices, thick PN junctions, for example, PIN junctions with very high breakdown. Records for MBE is in the top 5 in all literature for any technique. We replaced ITO, which has got a known problem of kind of non-uniform distribution of current and light-emitting diodes with these tunnel junctions to give much more uniform light. And we've even increased the percentage of indium, so we lowered the band gap of solar cells, which is a state-of-the-art in the field in terms of the III-Nitride solar cells. So with that, let me switch to the other side of my work, and I'm going to end in about 8 to 12 minutes. So if you're looking for that end, it is coming. I guarantee you the end of this will arrive. Most of this oxide work is currently done under the CEREBRAL MURI with a talented team of Georgia Tech folks here shown in orange and Binghamton University folks shown in green here. And the idea of this is simply this. If you have a cat, God help you if you do, but if you have a cat, you know very well that cats are about as useless as teenagers. Like teenagers, they eat your food, they poop in your house, and they cannot be trained to do anything. Whereas if you have a dog is substantially more intelligent and can learn tasks and do things. It doesn't just apply its brain power to exist and do things that it needs to do to survive, but it actually can be trained to do useful tasks. Now, the difference between a cat and a dog is roughly 1 to 3 billion extra neurons, that the dog has extra neurons to do new things, to learn new tasks. So the argument that we put forth here is that if we want to do some sort of emulation of what the brain does, we will probably have to have these neurons, whether they're circuits or a device or what have you, in the billions of neuron range to do useful things. And unfortunately, as I'll show you in a moment, silicon just cannot hope to do it at that level. So what we're trying to do is say, hey, can we replace a transistor? Now that's an impossible task, wouldn't you think? But can we replace a transistor with some nanoscale component that we can pack in at very high density that can replace a circuit with a lot of transistors with just one device, or maybe even encode the information that we're looking for at the atomic scale, written into the material itself, change its band structure. Band structure isn't that a constant of material science? Mother Nature gives you band structure, doesn't she? Well, the answer is no, you can modify band structure. And the argument basically can be seen here for the silicon, why we don't want to do with silicon. The Lodi chips that have 128 cores emulate about 131,000 neurons. That's actually a remarkable engineering accomplishment here. Okay, but if you look at that amount of power is about the neural power of a fruit fly. And to be fair to the fruit fly, it's actually about half the neural density of a fruit fly. So if you take these chips and you put them on a board and you put 32 of these chips in there and wire them up on a board, you actually improve things a little bit. You get about 4 million neurons and you're up to the level of a cockroach level of intelligence, okay? If you put a whole bunch of these boards together and you have 100 million neurons with almost 800 of these chips in there, you're at a hamster level of intelligence, and you better back this device up to a power company because you're going to be consuming enormous amounts of power. You're not going to put this on, say, a drone or put it in everybody's home and have this type of capability spread out in a car or anything like that. Those type of applications are very limited. So the argument is we want to basically shrink this down. Put all these circuitries that takes up a lot of space into a device. And the device that most people are looking at to do this is what's called a memristor. It's basically a resistor that remembers what current has flown through it in the past, and as such, it can change its resistance based on what its previous experience is. It basically learns, okay? And the one that we look at are these lithium-based memristors where we can put lithium in a crystal or take it out of the crystal. And the cool thing about this is we can do this with simple electric fields. We have metal contacts applied to this. We put a voltage across the device and we pull lithium out of the device. And in doing so, we literally change the band structure. Here's basically a picture of the density of states versus energy. So this is density of states versus energy here. And basically, by removing a certain amount of lithium, you can rapidly change the density of states. The density of states determines the properties of a material. Resistance, magnetic properties, all kinds of different things come from this band structure. We've proven this out in measurements. We've actually gone in and measured the density of states with various different spectroscopy methods at national labs. And we've even shown that you can convert, say, a direct bandgap material to an indirect bandgap material. So you have actually access not just to things like resistance and magnetism, but you can change the optical properties. Over the years, we've done a lot of work. We were the first ones to start this stuff when nobody was thinking about using lithium to do this. And there's been a lot of device innovations that are doing. And what you're seeing now is that there is a real takeoff in the published papers per year in this area. And this lithium ion intercalation is a really nice tool to do these advanced functions. One of the things we can do is we can have enormous resistance changes. They're linear changes. So they're not step digital changes like in a transistor. I can change the resistance by a set amount by just how many pulses I apply. And I can either allow that resistance change to relax after the stimulus is gone. That's a volatile change. Or I can remember that change non-volatile like memory. We don't remember every face we see. We have to process data, see what's important, and the ones that are important, then we come over and remember. So you need these different temporal functionalities to actually implement intelligence. You may not think about it, but an important one that you need is also midterm scale, if you will, forgetting, basically where you think something's important, like a girlfriend that you liked in high school, you think she's important, but after you get in college, you don't think she's quite that important, so you start to forget her a little bit, something like that. There's some cool other physics we can do, like the equivalent of NDR in other devices you could do with ensembles of lithium, where this momentum basically carries this lithium on in a particular direction as you switch voltage around. You can implement things like inductance this way, at low frequency inductance, which is counterintuitive, but that's what it basically is. Then we have to ask the question, can you use it? Does it matter? Is it something that's worth pursuing? And to do that, you basically have to say, will it scale down to these nanoscale sizes? get more devices per area, low power, and even make them faster when they get smaller? And the answer is it looks like they will. If you look at the scaling of these things, what's cool about our technology is they have some scaling that kind of follows CMOS rules. So the smaller you make it, the lower the power, the faster it goes, blah, blah, blah. All the same CMOS scalings happen. And we've predicted that they will operate with picowatt DC if you choose to do DC, or attojoule type energy switching applications in the future. So I promised you some failures. I want to take 2 minutes longer than I had hoped to live up to that promise. Basically, if you're doing something that nobody has ever done before, you are probably going to do some things that just are not going to work out. And this is one of the examples that I would give to one of my many glorious failures of attempting to do things and it not working out. Now, originally, we had this concept of, hey, let's take some UV light, let's put it on a specially designed Texas Instruments micromirror that can handle the UV light, and let's focus it on a wafer. If we do that, we can project an ultraviolet light movie onto the growing wafer, and instead of growing sheets of atoms, we can adjust photochemistry in real time, grow one composition of material in one region and another composition of material in another region at arbitrary ideas. And so here's an example of the micromirror that we had with the Air Force logo that paid for this on it. You got to make your sponsors happy, right? Just like NASCAR. Science is just like NASCAR. You got to keep your sponsors happy. And so when we did this, this was our first implementation. And the bottom line was it sort of worked. We could show that the chemistry part of it worked, that if we grew at a particular thermal energy temperature, an indium gallium nitride material, we did have indium gallium nitride, evidence of this little side peak. This is gallium nitride. This is indium gallium nitride right here. And when we turn the UV light on, we would have just gallium nitride, not the indium. The indium would not incorporate in the crystal. But as it turned out, the optics of this system, like coating of windows, getting enough power through a window, was so complex. We spent probably close to $25,000 on blowing up windows and changing optics. Was probably another $100,000, and we never really got it to the point where it was actually useful. And it turns out from a law of magnetism, so this goes into the fundamental limits, it was not going to be possible for us to do this at a nanoscale. You could do this in the fractions of a millimeter type scaling, but you could not do this at really small devices. And so it was later deemed basically, you can do it, sort of, but what you get out of it doesn't warrant the effort, okay? Now, a friend of mine that was working on this project, instead of using photochemistry, used photothermal. So he did a rastered laser. And the interesting thing was he went to my website, pulled up a picture of me, and he literally wrote it into the wafer with indium composition. So this is an SEM backscattered electron image that's sensitive to the Z number of the atom, basically. And he literally wrote the picture of me into a wafer here. And so it does work, but it is not that practical, okay? So the bottom line is, I'll give you my conclusion is overall, we've had a lot of fun here at Georgia Tech. It's a great place to work. If you're a new student here, welcome here. It's a wonderful environment with great people, great resources, really creative ideas. But the bottom line is, I encourage you to pick really difficult topics. Life is really fun, but you really got to go on that unbeaten path to really have a lot of fun. If you're going after chasing 1 or 2% on a new device or an existing device, you can probably make some money, you can probably get a job, but it's not nearly as fun as doing something that everybody else says can't be done. So with that, I will end, and I will guess David can relay to me the questions, because I can't hear you apparently. So
right. So I'm gonna let everyone in on a little secret. So you guys can hear me, and you can hear Professor Doolittle, but he can't hear me, which is an interesting thing. So the technology we came up with is that I now have connected to him with my phone, and I will relay the questions. So you go ahead and you can enter questions in the Q&A box. We have a couple already. So the first question is from Jonathan Goldman, who asks, how does MME growth rate compare to MOCVD or MOVPE growth rates?
So MOVPE, okay, first of all, it depends on the material. MOVPE is a growth technology that people will quote you, the commercial systems in the 5 microns an hour range. So it's comparable to MME. We can do 10 as a hero number. They can do 5, 6, 7 as a hero number. But the truth of the matter is, when you're doing a device, most people grow slower. I mean, most of the time when we're doing a device, we don't grow that fast because you want more control, and we grow something about 2.8 microns an hour. I'll put this in perspective. When people are growing bulk crystals, they use this method called a monothermal methods, and our growth rate for MME is actually fast enough to compete with it, meaning that we can actually grow bulk wafers, this stuff, and be competitive with that. So it's very, very high. And the other side of this is when you grow, say, a power device and you want to grow, say, 30 to 50 microns, these CVD systems, no matter what it is, typically has depositions that form on the chamber walls, and they start to have particulates that drop down into the film. And that's devastating for a power device to have these things incorporated into the film. In the MBE case, you can grow, 100 microns of material and never have that happen. So we believe, although again, it's counter to what is typically used today, there's over 10,000 MOCVD systems installed worldwide because they're cheap and they're really effective. But we believe there is a space for this new technology in the community.
Okay, we have another question from Chris Yang. He indicates this is cool technology. I'm not sure which part of it he's talking about, but when can it be transferred to the real world?
So we have a lot of people that are adapting this, and keep in mind, MBE systems are all over the world. There's thousands of them in various different modes of production. A lot of these came from the gallium arsenide and indium phosphide, optoelectronics, and electronics world. So they're already at manufacturing facilities. And a lot of these folks are now starting to pick up our technique and use it. Most of the big groups out there are doing some form of low temperature growth now, if not our approach, but some form of low temperature growth is really taking on now.
Okay, we have another question from Eric. It says, where do you see aluminum nitride fitting overall into the spectrum of power semiconductor applications? For example, can it have RF applications versus new materials like gallium oxide? Could this material potentially handle ultra high voltage switching for DC current applications?
Hey, you're dead on, Eric. That's exactly where we see this. One of the advantages of gallium oxide, one of the only advantages, is it has a reasonably high breakdown field and it has its own substrate. Well, it turns out aluminum nitride has way higher, about 50%, about 33% higher breakdown field, and it has its own substrate as well. But unlike gallium oxide, where you only have unipolar doping, you fundamentally, the band structure says it cannot be p-type, right? I just said that we can do the impossible, so if maybe somebody can overcome that. But the physics as we know it now says it cannot be p-type. We now have p and n type. So when you're talking about breakdown, if you are limited to Schottky barriers, you're limited to half of the theoretical breakdown from the first place, because you have half the band gap to work with a Schottky barrier. When you talk about a p-n junction, in aluminum nitride, you not only have a higher breakdown field, but you can use the entire thing because you can have p-n junctions. So we believe that aluminum nitride devices can be very important for grid level voltages, for example, in switching applications, power applications. Not to mention that gallium oxide is a terrible thermal conductance, so it may tolerate high voltages, but it's not a real good power device, right? Aluminum nitride is one of the best thermal conductivity materials we have in the semiconductor world. It's actually used as a heat spreader in some applications when they use it in polycrystalline form.
Okay, we do have another question, I think, which is basically the same, but this is from Habib Ahmad, who says, great presentation and wonderful achievements. What is your way forward for aluminum nitride-based research and its device applications?
Yeah, so the bottom line is once you have N-type conduction and P-type conduction in a semiconductor, the entire future is your animal, if you will. You own it. You can do LEDs, you can add in quantum wells, you can do transistors, you can do power devices, you can do photodetectors. I mean, what has happened here is that my group and my wonderful students that we have in our group actually have invented an entirely new field of science. This is so big of a deal that, I'm 55 years old, and I fully anticipate that this field of science will probably carry me through the time when they carry me out the door of Georgia Tech on a gurney.
Eric has another question about with aluminum nitride. What is the path forward for reducing defects? What kind of defect densities do you have now? I may have missed that. He may have missed that.
Yeah, so there's a particular defect we're dealing with now that we know engineering-wise what we need to do, but we just need to build the tools to bypass it. And the bottom line is aluminum nitride has a really stubborn oxide on it. So when we grow on these aluminum nitride substrates, the template that we do the epitaxy on, it is extremely difficult for us to get rid of that oxide on the surface. And we tried a few simple techniques, but it looks like the simple techniques are not going to do it. And we're going to actually have to build some tooling to emulate what the MOCVD people do at these ridiculously high temperatures. So not surprisingly, when we do things at low temperature, we want to emulate what goes at high temperatures. We do plasma processing, and that's where we're headed with that. So that particular defect is creating some stacking faults along the interface, the regrowth interface. And the edges of those stacking faults actually propagate some dislocations up. And that's actually why the breakdown voltage was fairly low in this first device. So we're hopeful that if we can get rid of that interfacial oxide, that we will be able to get rid of the stacking faults and the associated defect that is limiting breakdown at this point.
Great. I think, actually, in light of the hour, we're going to end there. I want to thank Professor Doolittle one more time for speaking today. It was an excellent seminar, and thank you all for attending, even the cat lovers among you who stuck with it after being insulted. And just a reminder that we'll meet again in 15 days on January 26th for the next NanoEdTech seminar. Stay safe, everybody.